All right, let's work through the practice test here. So my problems might be a little different than the problems you see when you work through the practice test in Hawks. They should be the same type of problems, but the numbers may be a little different. The examples may be a little different that they're giving you, but it should be basically the same type of stuff. Okay, so let's take a look here. This one says, identify the population being studied, and we're given the number of hours a group of 13 children in Mrs. Smith's kindergarten class play outside in a day. Okay. So the population is the whole group that we want to know about. So we're looking at 13 of the children in Mrs. Smith's kindergarten class, but what's the whole group we're studying here? We're looking at the whole big group, the whole population. That would be all the children in Mrs. Smith's kindergarten class. Okay. We're not counting anything about the number of hours children play outside, and all children that play outside is too big. Okay, we're only looking at the ones in Mrs. Smith's class, so can't be that one. And it also wouldn't be the 13 children, that would be a sample. Look at number 2. It says determine the numerical value describes a population parameter or a sample statistic. We're given the average price of a car at the new car dealership in town is $28,400. Okay. So this one would be a population parameter. That might seem a little tricky, but it doesn't tell us about taking a sample anywhere in there. If it said something like a sample of 58 vehicles at the new car dealership is taken and the average price is da-da-da, then that would be a sample statistic. This one is telling us about all the cars at the new dealership, so it's not a sample statistic. Okay. Number 3 is determine whether the statement describes a descriptive or an inferential statistic. This one says 50% of all students at the local university voted in the last election. Okay, well, this one is going to be a descriptive statistic. Okay, if it was an inferential statistic, it would have to say something about sample data and then use that sample data to make a conclusion about the whole population. So if this one was going to be an inferential statistic, it would have to say something like a sample of 20 students at the local university was taken, and 50% of those in the sample voted in the last election, therefore 50% of all students voted in the last election. You have to make some type of inference about the whole population based off sample data. We don't have that on this one, so we're just describing our data set. So it's a descriptive statistic. Okay. Number 4, and this one formatted a little weird for some reason, but we can do it. We want to classify the data, and we want to classify it all 3 ways. We're given the heartbeats per minute of 40 randomly selected people. So if we're counting the number of heartbeats per minute, would that be qualitative or quantitative? Okay. We're counting, so that's going to be quantitative. Okay. And would these data be discrete or continuous? Well, or neither. Right? If it was qualitative, it would be neither. So which one could this be? Since we're counting, we're not going to count 25.5 heartbeats. You could calculate that, but this one says we're just counting. So only our counting numbers make sense, not numbers in between. So usually when we're counting, we're dealing with discrete data. Okay? It wouldn't make sense for us to think we could get something like 25.47 beats per minute. You can't count that. Okay? And then it's not qualitative, so it's not neither. Okay, and then what's the highest level of measurement? Well, we said it's quantitative, so it's got to be either interval or ratio. All right, so we can mark off nominal and ordinal here. So the difference between those two is for ratio level data, 0 actually means the absence of something or the beginning of something. So what does it mean if you have a heartbeat of 0 beats per minute? That means your heart's not beating, right? The absence of a heartbeat. So this one is ratio. It's ratio. Because 0 actually means 0, actually means nothing. And here's another similar one. This time we've got the heights of 48 randomly selected female students. Okay. Well, if we want to get height, we would measure that. So again, this would be quantitative. And since it's quantitative, we can decide if it's discrete or continuous. And it makes sense to say someone is 64 inches tall or 64.12 inches tall. You can be as precise as you want to be, and it's a measurement. So this is continuous data. Okay. And then again, for the last one, since it's quantitative, it's either interval or ratio. So what would having a height of 0 mean? That would mean you actually had no height, right? You were 0 tall, right? That means you don't have any height at all. So this one would be ratio again, okay? Not interval. Okay. Number 6 says weights of animals are an example of which type of data. So we're just having to kind of do some thinking on our own instead of doing all the steps here. We're looking at the weights of some animals, so we would measure that. Okay. So if we have a measurement, it's quantitative, and measurements are continuous. Continuous there, so that one would be continuous. Number 7, got religious affiliations. Well, first of all, would that be quantitative or qualitative? So we're talking about things like your religious affiliation would be Christian, Muslim, Hindu, something like that, right? So those are labels. Okay, so this would be qualitative data. Terrible use, sorry. Qualitative data. So since it's qualitative, it's going to be neither one of these. It can't be discrete, it can't be continuous because it's qualitative. It's just a label. Okay. Number 8, we're filling out a frequency distribution. We got the percentage of satisfied customers at Joe's Used Cars. We want to complete the frequency table. And so our first class, we're dealing with data between 83 and 85.9. So any data value 85.9 or smaller, we're going to count that. So what I do is I just go through the data and mark it off if it suits that. So we're looking for any data smaller than 85.9. So there's one, there's one, there's one, there's one, there's one. And I think that's all. So 1, 2, 3, 4, 5. The frequency there. Okay. So now when we go to the next one, we're looking between 86 and 88.9. Since I've got all those other ones marked off, all I'm going to do is I'm going to look for ones that are less than 88.9. Okay, so there's one, there's one, there's one, there's one. Okay, so what do I have? 1, 2, 3, 4. Okay, so now we want between 89 and 91.9, so I'm going to look for any data value that's left that is smaller or equal to 91.9. Let's see. There's one, there's one, there's one, there's one. So 1, 2, 3, 4. Okay. I'm running out of color, so I'll go back to red, I guess, and we'll circle it or something. So now we want between 92 and 94.9. So anything 94.9 or smaller, I'm going to mark off. So there's one. And that's the only one I see. And I said I was going to circle that. Okay, so there's one. And then now we've got everything that's left if we've been careful. So now we want anything smaller than 97.9, so or equal to. So there's one, there's one, there's one, and there's one. So 1, 2, 3, 4. And then it's a really good idea when you get finished to make sure you haven't missed any to add up your frequencies. So 5 plus 4 is 9, plus 4 is 13, plus 1 is 14, plus 4 is 18, and then count and make sure that's how many you had. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's just a good check to make sure that you didn't actually accidentally skip over one. Okay. There's our frequency table. Okay, this one says the following data represents the distribution of ages of a group of people. Determine the graph that correctly represents the data. And let's look at the top two first. Okay. All right, right away, I know it's not the first graph. How do I know that? Well, it doesn't have any labels. And so if we don't have labels, that's not going to be a good graph. Okay, if we look at the second one, okay, that's looking promising. So I'm going to maybe come back to that one. Let's look at the third one. I'm looking at this one down here. Okay. So what's wrong with that one? Well, that one says that the last class is frequency of 6, but if we look at the table, it's 2. So that the data just doesn't match the table there. Okay. And then what's wrong with the last one? Well, this one's a bar graph. It's not a histogram. And we would want a histogram for a frequency distribution. So here's our correct graph. You just can kind of do process of elimination if you're not sure. Okay. Sorry about that. Number 10. We didn't skip any, did we? Let me make sure. Okay, no. Number 10, stem and leaf plot. Okay. Got the distribution of weights for a group of people. Step 1 says, what is the weight of the lightest person? Okay, well, the smallest stem is 11. And then the smallest leaf there is 2. We're dealing with weights, so the lightest person is going to be 112. Step 2 says how many people weigh in the range from 110 to 170 inclusive. Okay, so if we start at 110, that would be 110, and so that would start here. So we're going to count the first row, second row, third row, fourth row, fifth row, sixth row, and then if we have anybody that's 170, we don't. So we're counting all of these. Okay. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So if we had a 170, so if we had a 0 down here, it says inclusive, so we would include the 170, but we don't have one of those. And 173 is too much. Okay, and then the last one says, what is the weight of the heaviest person in the range 150 to 159? So we're looking at this row. So what's the heaviest person? It's 157. That's our biggest leaf. So our heaviest person here is 157. All right, number 11. We're finding mean, median, and mode. Okay, so step 1 says determine the mean. How do we figure out the mean? Okay, we add them up and divide by the number of data. Okay, so our mean here, we punched that in the calculator, so we got -5 minus 6 minus 13 plus 5 plus 0 minus 1 plus 14 equals 8. Divided by 1, 2, 3, 4, 5, 6, 7, 8. We have 8 data values. So our mean is 1, and if we're being picky, we would say 1.0 because we're using our rounding rule. Okay. Want to determine the median next. Okay, so before we can find the median, we've got something we've got to do. We've got to put the data in order. So you can either do least to greatest or greatest to least. So let's see, we've got -13, -6, -5, -1, 0, 5, 14, and 14. Make sure we didn't miss any. 1, 2, 3, 4, 5, 6, 7, 8. That should be all. Okay, so now to get the median, sorry about that, to get the median, we want the middle value, so we can mark numbers off on each end. And this is a case where we have two middle numbers. We got -1 and we got 0. Okay, so we would do -1 plus 0 divided by 2. And so our median, we get -1 divided by 2 is going to be -0.5. Or if you put -1/2, that's okay also. If you have exactly one number in the middle, that number is the median. In this case, we had to work a little harder. Okay, and then step 3 says find the mode, and is it unimodal, bimodal, or multimodal, or no mode? Okay. Here we have 14 is on there twice. Okay. That's more than any other data value, so our mode is 14. We only have one mode, so this is unimodal. Okay. Number 12 is for the graph shown, determine which letter represents the mean, the median, and the mode. Okay. I start with the mode because the definition says the mode is the tallest point on the graph, so the tallest peak on the graph is right here at C. So that's the mode. Then I go to the mean. The mean is going to be the one that's closest toward any outliers we have. The shape of this distribution is skewed to the right because somewhere out here we have at least one outlier. That's why our data is skewed. So the closest value to that would be B. And that's the closest to the mean. To the outliers. And then the one left over is the median. Okay, the definition says it divides the area under the curve in half. That's not real easy to see if it's skewed. That's why I do those in that order. Okay, number 13 is for the following type of data set. Would you be more interested in looking at the mean, median, or mode? State your reasoning. So we've got the price of cars on the car lot. So this would be quantitative data. Okay, so that's going to be part of my reasoning. We've got quantitative data. And then would we expect outliers or not? So we just have a random car lot. And so on random car lots, usually they have some real expensive car that they have, in the showroom to show off, to try to get people's attention. And that's going to cost a lot more than many of the other cars. So it's possible we would have outliers here. So since we have quantitative data with possible outliers, what should we use? We should use the median. If we did not expect outliers, we could use the mean, or if we had qualitative data, we would use the mode. Okay. Number 14. Number 14 is just a calculator problem for the most part. It says find the sample standard deviation. Okay, so that's going to be S. Or a lot of your calculators will call it SX, or maybe some of them will call it sigma n minus 1. Okay. So I'm going to pause for a second and put this data in my calculator, and we'll come back and talk about the answer. Okay. Make sure you check over your data, especially when you have this much data you're typing in. Check back over your data values, make sure you haven't made a typo. So for my calculator, I've got sample standard deviation 1.038457, on and on and on. It says round to one more decimal place than we had in the data. So if you look at our data had one digit after the decimal, so we want 2 digits after the decimal. So when we round, we're going to round the 3 up to a 4. Okay. Have a sample standard deviation of 1.04 degrees. Okay, so you just need to make sure you can do standard deviation in your calculator. Number 15 Suppose that the diameters of a new species of apple have a bell-shaped distribution with a mean of 7.25 centimeters, standard deviation of 0.42 centimeters. Using the empirical rule, what percentage of the apples have diameters that are between 6.41 centimeters and 8.09 centimeters? So the way I like to do these, and you don't necessarily have to work them this way, but the way I like to work these is to label everything. So it says my mean is 7.25. And then I'm going to figure out where 1, 2, and 3 standard deviations above that, and 1, 2, and 3 standard deviations below that will be. So my standard deviation is 0.42. So 7.25 plus 0.42 gives me 7.67 plus 0.42 again. I get 8.09 plus 0.42 again. I get 8.51. Now I'm going to take 7.25 minus 0.42. I get 6.83 minus 0.42 again. I get 6.41 minus 0.42 again. I get 5.99. So here's my mean. This is 1 above, 2 above, 3 above. This is 1 below, 2 below, and then 3 standard deviations below the mean. This one we want to know what percentage of our data is between 6.41, 8.09 centimeters. Well, that's within 2 standard deviations of the mean. So the empirical rule says we should have 95% of our data in that range. Okay? I'm not going to give you one of the real hard ones on the test. The main thing I want you to remember, okay, is within 1 standard deviation, we've got 68% of our data. Within 2 standard deviations, we've got 95% of our data. And within 3 standard deviations, we've got 99.7% of our data. So it'll be one of those. But you need to be able to show me how you figure it out and then give me the percentage. Okay. All right, number 16. It says calculate the 5-number summary of the data. All right, so we've got to put our data in order here. So let's see. We got a 1, a 2, 3, a 4, 5, and a 6. Oh, I missed a 2 here. I've got to have 1, 2, 2. All right, so 6, 7, 8, 9, 10, 11, 12. We do have a 13. We do have a 14. We do have a 15. We do have a 16. 17, 18, 21, and a 22. Let's count, make sure we got all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, it's important we don't miss one. Okay, now we want Q1, Q2, and Q3. We also want the minimum and the maximum. That's the 5-number summary. Okay. And remember, Q2 is the same thing as the median. Okay. So first I'm going to find Q2. So I'm not going to mark these off just so it messes things up on the screen. I'm just going to use my fingers and count, hopefully without touching the screen. So what's our middle value? It looks like our middle value here is 13. Okay, so then we split our data into the lower half and the upper half. Okay, so that looks good. So then the median of the lower half of the data is 3, so that will be Q1. The median of the upper half of the data is 17, so it's just like finding the median of those two pieces. And the minimum is 1, and the maximum is 22. So there's our 5-number summary: 1, 3, 13, 17, 22. That's using the approximation method. Okay. Number 17, find the expected value of the following data. So the expected value, here's the formula. Okay, it looks messy and it's kind of confusing if you're not used to looking at the notation. It says it's the sum of each probability of each outcome times the probability of each outcome. I'll get right in a second. And so that formula is confusing if you're not used to looking at that. You can just remember how to do it. Okay? So all we're going to do to get expected values, we're going to take each outcome. My first one is 3, multiply it by its probability, 0.2, plus my next outcome of 4 times its probability of 0.3. We just keep doing this for all of them. So plus 5 times 0.1, plus 6 times 0.2, plus 7 times 0.2. Okay. And we put that in our calculator. 3 times 0.2 plus 4 times 0.3 plus 5 times 0.1 plus 6 times 0.2 plus 7 times 0.2. And for our expected value, it says round to 1 decimal place. That's how many I got. So our expected value here would be 4.9. Okay. Number 18. This is the messiest one. Just find the standard deviation. And for a probability distribution, it's not the same formula from chapter 3. Okay, this one says we want the sum of each outcome squared times its probability. And then we're going to subtract the mean squared. That's also known as the expected value. And then take the square root. Okay? So this mean squared, is the same thing as the expected value squared. The first thing we want to do is get the expected value. Okay, so this is just like the last problem. 7 times 0.1 plus 8 times 0.2 plus 9 times 0.3 plus 10 times 0.2 plus 11 times 0.2. If we punch that in our calculator, I'm going to pause for a second. Okay, we get 9.2 there. Save that number, we're going to have to use it again. So now to do standard deviation, we're going to do almost the same looking formula, except each outcome is going to be squared this time. So we'll have 7 squared times 0.1 plus 8 squared times 0.2. A little sloppy there, sorry. Plus 9 squared times 0.3 plus 10 squared times 0.2 plus 11 squared times 0.2. Okay, and then we got to do this part. So minus 9.2 squared. Okay, and then we got to take the square root of all of that. Okay. The way I like to do it is I like to do the part just underneath the square root first. So let me calculate that. Okay, so underneath the square root, I'm getting 1.56 Then if we take the square root, 1.56, I'm getting 1.2489996, and it says round to one decimal place, so that'll be 1.2. Our standard deviation. So a little messy, but it's not terribly difficult. It's just a little long, a little messy. Okay. 19. Okay, so we're trying to find the expected value of this bet here, but we don't have a table. We got to make our own table. So we need each outcome. We need the probability of each outcome. So it says if we draw a card with a value of 3 or less, they will pay us $14. So that means we'll win $14. If we draw a different card, we have to pay $6, so that's -6. Okay. Now we got to figure out the probabilities. Remember, there are 52 total cards in the deck. It says aces are high cards, not low cards. So how can we get a 3 or less? That would be drawing a 3 or a 2. So there's 2 ways in each suit. Okay, but there's 4 suits, so we have a total of 8 winning cards in the deck out of 52. And then if we do 52 minus 8, that tells us we have 44 losing cards out of 52. And then we want the expected value here. So that will be 14 times 8 out of 52 plus -6, and it's okay if you do -6 there, times 44 out of 52. And we're dealing with dollars, so it says round our answer to 2 decimal places. So 14 times 8 divided by 52 minus 6 times 44 divided by 52. I'm getting negative 2.9230 something. So when we round to 2 decimal places, get negative $2.92. Step 2 says if we play the game 740 times, how much would we win or lose? Well, it's negative, so we're going to lose. So we do negative $2.92 times 740 times making the bet. We're going to lose a lot of money. Let's see how much. So negative 2.92, we can expect it anyway, times 740 equals, we expect to lose $2,160.80. Bad bet, don't make that bet. Okay. Number 20 says a quality control inspector has drawn a sample of 14 light bulbs from a recent production lot. If the number of defective bulbs is 1 or more, the lot fails inspection. Suppose 10% of the bulbs in the lot are defective. What's the probability the lot will fail inspection? Okay. So a bulb is either defective or it's good. Only 2 possible outcomes. So this is a binomial distribution. So if we're dealing with a binomial distribution, we need our 3 numbers. We need n, p, and x. So n is the sample size or the number of trials. So we are going to test 14 light bulbs. So that's n. P is the probability of success on 1 trial. So we're calling a success a defective bulb. It says 10% of the bulbs in the lot are defective. So P is 10%. Or 0.1. And we're trying to figure out the probability the lot will fail inspection. That happens if we have 1 or more defective bulbs. And so that would be x greater than or equal to 1. Okay. So you can do these with your calculator if you have a graphing calculator. If not, I will print out and give you the pages in the tables that you need. So what I'm going to do is I'm going to go over to Hawks and we'll look at the tables in Hawks. Okay, but I'll have these printed out for you. So 1 second. Oh, so we should mention, since we want not equal to some number, but greater than or equal to some number, okay, then we will use the cumulative binomial table. But wait a second though, because the cumulative binomial table gives us the probability of being less than or equal to some number. So if we flip this around, probability of x being greater than or equal to 1 is the same thing as 1 minus the probability of x being less than 1. Okay. And less than 1 is the same thing as what? X being equal to 0. On this one, we can actually use just the regular binomial table to find the probability that x is 0. So n is 14, p is 0.1. We're going to look up an x of 0. So go to the binomial table. N is 14, p is 0.1, and we want x of 0, so 0.2288. That's not our final answer. We want 1 minus 0.0, what was it, 2288? I'm sorry, 2288. So what do we get there? 1 minus 0.2288 equals 0.7712. Okay, 0.7712. All right, let's look at 21. 21 says a certain insecticide kills 50% of all insects in laboratory experiments. A sample of 7 insects is exposed to the insecticide. What is the probability that exactly 4 insects will survive? So in here, we got 7 insects. P, have to be a little careful on this one. It worded this one a little tricky. Well, we would be okay because it says it kills 50%. We want to know what's the probability 4 insects survive. So 1 minus the 50% killed is 50% that survive. So P here is going to be 0.5. And then what are we looking for X? We want exactly 4 insects to survive. So we want X to equal 4. You can use the formula for this one if you want to. But I'm just going to use the tables again here. So N is 7, P is 0.5, X is 4. So we're still in the binomial table. But this time N is 7, P is 0.5, X is 4. So our probability here is 0.2734. So our probability. Okay. One more problem here, I think. Yes, last one. Okay, this one says a quality control inspector has drawn a sample of 11 light bulbs. Suppose 70% of the bulbs in the lot are defective. What is the standard deviation of the number of defective bulbs? If we have a binomial distribution, our standard deviation, square root of n times p times 1 minus p. Okay. So n here is 11 light bulbs. P is 70% or 0.7. 1 minus p will be 30% or 0.3. Okay, so we've got 11 times 0.7 times 0.3. So underneath the square root, we have 2.31. When we take the square root, 2.31, we won't round yet. We get 1.5198 on and on. But it says round your answer to 2 decimal places, so this will round up to 1.52. Okay. All right, if you have questions on any of those, let me know. Good luck. I'll see you on test day.